Hello, welcome to my term paper presentation. We will discuss in this presentation about quantum Hall effect. So let's get going. For the first time, quantum Hall effect was observed in a two-dimensional electron gas when a magnetic field was passed through it in a perpendicular direction. So to discuss this elusive phenomena, first of all, we would just recap a bit of classical Hall effect. Classical Hall effect, we know how it arises. It's just electrons moving in a sample perpendicular to the direction of the applied electric field. The Hall resistivity can be calculated using the root model as shown here. Rho xy is equal to V by Ne. This is the transverse resistivity, which is also known as the Hall resistivity, and then the longitudinal resistivity is given as it's written here. So what is quantum Hall effect? For that, we explore two experiments that was done in the 1980s. The first experiment is the von Klitzing experiment. It was performed by von Klitzing, Doda, and Pepper in 1980s. They observed two different phenomena that we have actually never seen before in a two-dimensional electron gas. They observed, first of all, that the Hall resistivity is quantized. So the Hall potential forms plateaus when the gate voltage is tuned from 0 to higher values. And they also observed that when these plateaus do form, the longitudinal resistivity goes to 0. Using this observation, they claimed that the Hall conductivity was quantized in the units of E squared by h. After this experiment in 1982, we have the Sui and Stormer experiment. In this experiment, Sui and Stormer observed that N0 can take fractional values also. As you can see in this adjoining graph, that the Hall characteristic Hall plateaus form at nu is equal to 1 by 3 or N0 is equal to 1 by 3. In this paper, they described that the most prominent Hall plateaus were at N0 equal to 1 by 3, 1 by 5, and 2 by 5. Also, an interesting thing in this graph is that as we increase the temperature, these plateaus become more and more less prominent. So when the temperature goes above 4.15, they say that the Hall resistivity or the conductivity returns to be a straight line as described by the root model. So how do we understand these effects? So first of all, we see that there is an integer effect that the von Klitzing experiment described and a fractional effect which the Sui and Stormer experiment described. So first of all, we look at the integer effect. The integer effect is can mainly be explained by looking at the electrical transport in quantum mechanics. To see this, we solve for a charged particle in a vector potential A in the Landau gauge. A is equal to x b y cap. Solving this simple problem, we see that the energy levels are quantized, and this quantization we call the Landau levels. Now, building upon this problem, when we do it in presence of an electric field, we can, when we try to calculate the current, we can find that the current itself is quantized. From the current, we can get the charge density, which allows us to calculate the resistivity matrix. And from that, we get that the resistivity is indeed quantized in the transverse direction, with longitudinal resistivity being 0. We can explain all this and we can say that, yeah, this is how it happens, but we still don't know that why should these plateaus actually exist. And in the calculation that we saw, we have like very clean, we did not assume that there were any disorder. We assumed that the sample was translation invariant. So what happens if there is disorder? How do we explain it then? So in the presence of disorder, both the spatial extent and the energy of electronic states will change. Hence, we can say that the band of energy Landau levels can be considered to be spread out in somewhat of a Lorentzian peak, like that we show here in the figure below the top figure. This can be shown if we treat disorder perturbatively and write down the full mathematics. Now, what happens when this happens? So when we do the mathematics, we see that the extended states can only form at the peaks of these Lorentzian profiles, and all other states will be localized. If that is the case, then we can understand why these plateaus may form. Because as the Fermi energy is tuned through these levels, we see that we can expect that if only the star-marked electrons, star-marked states can conduct, the Hall resistivity or the conductivity will definitely jump discontinuously. But again, now we need to ask ourselves, if these states are there, where are these states actually localized? So, where are these states actually exist? So, to answer this question, we look at a phenomena known as edge currents. So what are these edge currents? So, if we look at this figure, then we see that if we pass a magnetic field through it, we see that all currents in the bulk of the material will just go to zero. They will just vanish. But the current at the edges, the electrons at the edge, they can't really form a full circle. So what will they do? They will start skipping around, like shown here. These electrons can carry the current. Only and only these electrons can carry the current. So we can say that the Hall effect, the integer Hall effect, is simply the quantization of these edge currents. And this statement was shown in 1981 by Halperin, that these edge currents are definitely quantized in the units of E square by H. Okay, now we can go to understand. We can try to understand the fractional effect. So let's go to the fractional effect. Yeah. So what is really the difference between the integer and the fractional Hall effect? In the integer Hall effect, we considered that the electrons were free. There were no interaction between them. In the fractional Hall effect, we will consider that there is a Coulomb interaction between these electrons. We know that the interaction term is easily given by this, as we have always seen for so many times. But the crux of the matter is that this potential is not easy to solve at all. However, in 1983, Laughlin solved this using this interaction term. They solved the problem of electrical transport for the new values equal to 1 by m. He proposed the wave function that we just show here, and this wave function is really, really complex, and it's very difficult to calculate with it, but it can be shown that this wave function represents the nu is equal to 1 by m states, which is done in my term paper, and this wave function represents partially filled Landau levels. So what are these fractional states actually? What do these fractional states represent? Is this some new state of matter? Many papers have talked about that these states can be considered as a liquid. So so this can be considered as a liquid. In 1985, Gerwin showed that the excitation spectrum in the fractional Hall effect is analogous to the excitation spectrum in superfluid helium. So if one wants to know more about how this is a liquid, they can refer to this. But this discussion was for nu is equal to 1 by 3. What happens 1 by m? I'm sorry for this mistype here. I wanted to say that what happens beyond nu is equal to 1 by m. I wanted to write 1 by m here. So deviations from this nu is equal to 1 by m ratio can be regarded as perturbations in the Laughlin liquid theory. To understand how this perturbation might work, we can say that we pierce the sample at Z0 with this thin solenoids. Thin solenoid will create a change in field at that point, and then the wave function will change accordingly. If you look into my term paper, you can see that how this change is mathematically incorporated, and then we call the new wave function with the change in charge density of Z0 as showing the existence of quasi-holes or quasi-electrons. In conclusion, the only thing I would like to say is that quantum Hall effect is a window into a rich world of exotic physics. This, what we described in this presentation and in the term paper, is just a very short review of the topic. It just looks into the first experiments conducted for quantum Hall effect and how people tried to explain those experiments. But to truly understand this effect, we need to look into the ideas of topology and geometry that play out in quantum many-body systems, which is completely out of the scope of this presentation. So, thank you for listening to my presentation, and I wish you a good day. Thank you.